Well, this will be the last topic within constraint optimization. We're going to talk about interior point methods, or at least some of the ideas behind interior point methods. We spent the last couple times talking about sequential quadratic programming. This is another modern method that's used. But before we get to that, or at least the ideas behind it, we're going to go back to a simpler approach. We're going to review penalty methods and discuss an interior penalty method that will motivate, at least help motivate some of the ideas of today. And this will also serve a bit as a review. So remember, the idea with the penalty function is that we could take our objective, f of x here, and we could add to our objective some sort of penalty term. And the idea was that when the constraints became violated, this term should become bigger, and that would cause the optimizer to try to drive this to zero. And we saw this was an imperfect approach because, well, for one, we need this parameter here, right? Because if there's no parameter, the optimizers, even with the parameter, it's always going to balance these in some way, right? So there's a trade-off, and this isn't always going to get exactly to zero. In the case that we did before, we had to make mu really big, right? It wasn't until mu went to infinity this would actually work, or exactly. And so we'd have to solve a sequence of these problems. And so we did what's called an exterior quadratic penalty. And I'll just show the inequality constraints here. Let's be a plus. And we added a 2 arbitrarily just for convenience. And we're going to sum these constraints and we square them. So the idea was that, remember, our constraint is that G needs to be less than or equal to 0. So if G is negative, that's great, right? We don't want to penalize that. So that's gonna, this is negative, this whole term here is 0. I don't add any penalty at all. But as G becomes positive, this is bigger than 0, and I square that. And the only reason why I square that is that if we didn't square it, let's say this was where the penalty started, we'd have this sort of discontinuity in the derivative, and having the squared term just makes it smooth, right? So that it comes in smoothly at 0. Okay, so that was a review. What we're going to do today is a different approach. We're going to use a barrier method or an interior penalty instead of an exterior penalty. And there are several forms, but I'm just going to show you one today. And it's going to look like this. So this is going to be an interior. It's a log penalty here. So if you could try this, if I said, let's try and make a penalty out of a log, you could play with it a little bit and you'd come up with this. You could, it might be worth pausing and just trying that a little bit, see if you could make a penalty with a log. But it's gonna end up like this. We take our objective and it's gonna be a minus mu times the sum over our constraints, and we're gonna take the log of each constraint. Okay, so remember that the log function is only defined for positive numbers. So what this is going to do is actually going to force this constraint to stay negative because I have that negative sign in there, right? So what it means is once G is negative, is feasible, it will always stay feasible because nothing else is going to be allowed by the log. It's maybe not obvious here. Let me show you what this looks like. Maybe we'll flip back. You can ignore the blue. This is another type of interior penalty method, but here's the red. This is that logarithmic barrier. So here's my constraint. This is a plot of just this this portion here, the minus log of minus G. Okay. Ideally, I want my penalty. You can think about, well, let me ask you that. What do you think ideally this penalty should look like? So this is on the x-axis G, right, my constraint, and this is my penalty. What should it look like? Well, remember, if G is negative, that's great. I don't actually want it to have any penalty, and I don't want G to increase beyond here. So I would like a penalty function that was just, let me make this thick here, which was 0, well, that's way too thick. Try that, which is 0 for a long time, right, all the way to here. And then it forms this huge barrier, right, which is like, you can't cross this. So maybe it's going to be very slightly smooth so that as you evaluate the function, there's no penalty, and all of a sudden there's a huge penalty and the optimizer is going to back away. And this may be a perfect penalty. And here's this logarithmic barrier for some value of mu that's approximating that. So what that means is that if I start here in this feasible region where G is negative, I can never cross this because the objective just gets so large that it doesn't matter what F is, right? What this little f is, it's never going to go across here because this just goes up to infinity. And it's also not obvious from this, again, so I say it's maybe worth plotting and trying this for yourself. But this becomes sharper, or as we saw, that it's kind of sharper where this becomes like 0 and then even steeper as mu goes to 0 rather than as mu goes to infinity. So we still would have to solve a sequence of problems, but rather than increasing mu, we would have to decrease mu towards 0. And every time we do that, right? So if mu is let's say pretty big, this barrier, I better make that thin again. It's going to be much shallower. It's not very steep. Okay, and as I decrease mu towards 0, it sharpens up like this and eventually becomes, really, really sharp. It's a very strong barrier. So we call these interior penalty methods also barrier methods because it's like a barrier that once you start feasible, you will always remain feasible. Here's a picture of what one might look like for, again, the simple 1D problem. So blue here, this is kind of like we looked before with the same functions looked before with penalty methods. Unconstrained, the minimums here. I have this constraint. This is 1D, so it can't be on this side. The solution is obviously right here up on the line. But if I added the penalty, the interior penalty, and I just added some, let's just start with this mu here, I'm going to get a function that looks like this. And you can see it's modified the function everywhere so that it has this sharp barrier here, and it's changed the function even below. You could see that here, right? See how it's decreased the function here? It's done that here as well. It's decreased the function so that the minimum exists somewhat close. And now as I decrease mu is going towards 0, we can see that that curve becomes sharper and sharper, and I get closer and closer to the true solution in this case. So interior penalty methods, they're going to have the same kind of problems that we had with the exterior penalty. One of them, namely, is that I'm going to have this ill conditioning. I'm creating this really, really sharp curvature in some direction, and so my Hessian's going to become more and more ill conditioned. It's going to become harder to solve. So we still have to do this sequence of problems. The other is like the exterior penalty methods. Remember how we're always going to be slightly infeasible, at least. Here we're always going to stay. We're always going to leave something on the table. We'll never quite make it to that boundary, but we'll always be on the feasible side. That could be an advantage, right? Because for some problems, even being a little infeasible would be bad, and so we'd rather err on this side. The downside of this method, though, as I've kind of hinted at, is that we can never go infeasible here. That also means you have to start feasible. And that can be hard. That means you have to provide a starting point that's feasible. And sometimes that's difficult. For some problems, it's hard to even find a feasible starting point. And so being able to provide one can be a challenge. So at least for the penalty method, this is a very simple algorithm. It's exactly the same as we saw before. For the other penalty, we'll have some convergence problem. We're going to minimize that f of x function, and we'll assign the result of that to x star. And actually, we'll just call it xk plus 1. That'll just be our next iteration. And then we take our penalty term, and we're going to, this is exactly the same algorithm as last time, basically. The only difference here, of course, is f is different, but the other difference is that rho is now a number less than 1 rather than bigger than 1, because we're decreasing it at each iteration. And that's really it, right? It's a basic method, but again, it has all the same kind of problems that penalty methods do. It's not a great method, but it has, it'll motivate some ideas we'll look at. So before we do that, let's look at an example in 2D. 1D is a little bit sort of basic. So here's a 2D example, just a quadratic function, a linear constraint. And it looks like this. Blue is the quadratic function. Here's the constraint. This is an infeasible side. Here's the optimal solution. So what I'm going to do now is I'm going to form that log penalty function. I'm just going to plot what those contours look like. Here it is. Here's what it looks like. Ignore the dashed line for a second. You can see the minimum of this now unconstrained problem, because we've got the penalties here. It's not quite at the true solution, but it's getting close. You'll notice I've got tons of these contours that are really close together. It's really sharply changing. You know, that's in part what's going to make these problems harder to solve. This dashed line means I'm just showing you a slice. So if I took a slice, I looked at the function value along this line and plotted it, that's what this looks like. And so you can see that barrier where it's really increasing sharply. So I have to start feasible. I can't start here. I have to start in a feasible region, but it's never going to cross this barrier. It just gets way too sharp. But you know, it'll search in the space and find a minimum. This is not the true answer as we saw, right? So I have to decrease mu even more. And if I did that, you can see it gets even sharper, right? And I do a sequence of those until, you know, I reach some whatever tolerance I'm happy with. So again, just to contrast, here's that 1D case. Here's our original function. The exterior penalty, as we saw, it doesn't change anything on the inside, but it's always going to be slightly infeasible. The penalty starts on the exterior. The interior modifies the entire of the interior, so it makes this big barrier and decreases the function out here. So it's going to give me a solution that's always on the inside. It's always going to be feasible, which is nice that it's feasible. The downside is I have to start feasible. Okay, so penalty methods, you know, they're great. Well, and I should say this about penalty methods. One other reason why I introduced them, although we don't use them for constraint optimization directly anymore, they'll be useful starting next time. We're going to start talking about gradient-free methods. And as we'll see, most of the gradient-free methods don't have any native way to handle constraints. A few of them do, but the majority of them don't have any mechanism for dealing with constraints. And so we typically have to form a penalty function to give to the gradient-free optimizer. We have to give it an unconstrained problem. And so these techniques of like an exterior penalty or a interior penalty are used in that context. That's less problematic in that case because again, the gradient, well, not again, we haven't really talked about it. In the gradient-free context, we're not going to get a super accurate solution. I mean, for one, we don't have a gradient, and that's how we know we've reached the optimum. And so that's okay, right? We're not necessarily, we're going to give up something there in exchange for maybe some more flexibility, but sort of this approximate objective is going to be kind of a good fit here in this gradient-free sense. So penalty methods are used there. There's another place that we in part use them, and I'll show you that in a second. We still use them here in these as part of the algorithm in these constraint optimization. Okay, so that was penalty. Let me move to the actual problem that we're going to do, or the actual method. This is called an interior point method. And again, I'm not going to work through the entire algorithm, but just the main detail here. So instead of forming an objective where we put everything in the all the constraints in the penalty, we're going to do something a little different. We're going to use a slack variable, and this is a relatively small change, but it's going to make a big difference. So it's going to be like a penalty. We still have f. We still have this minus mu, and we're still going to have this sum. I'm going to use k because that's what I did in the book. And we're still going to have this log term here. Just use a natural log, I guess. So all of this looks exactly the same, but instead of putting in here a constraint, like a minus g, instead of putting in the minus g, I'm going to put a slack variable, okay? And then one of my constraints is going to be, actually, let me just write that earlier. I'm going to have two sets of constraints. First is the equality constraints. Those don't really change. We don't have to do anything with those. The other is that now I'm going to have this constraint, g of x plus the slack is equal to 0. Okay. So notice that if I had solved this for the slack, right, if I just did the algebra, s equals minus g, I'd plug it in. That looks exactly the same as what we just did, right? I mean, in some sense it is, but it's not exactly the same. We actually have now this degree of freedom because now the optimizer has this extra variable. I don't have to have g be negative at every iteration. I do have to have s be positive. So this is an implicit constraint here. S is going to be positive. That's just actually not even really equal to 0. It's going to be positive just because that's how a log works, right? We're going to start with some positive slack and we'll never be able to cross that barrier just like we saw. But the nice thing here is that I don't have to satisfy, I can start with an infeasible point. I only need to satisfy, at the end of the problem, of course, need to satisfy this constraint. But just like we've done with constraint optimization in the past, as you've seen, as you've iterated, at intermediate solutions, the constraints don't have to be satisfied. So that's a huge advantage, because that means I don't have to provide a feasible starting point. I can provide any starting point, feasible or not. And this is still gonna work for us. I'm forcing these slacks to be feasible, which are, like I said, a degree of freedom that the optimizer can play with, right? Eventually, of course, at the solution, we know all these slacks are going to be exactly equal to minus g. We know what they're going to be, but that's not, doesn't have to be there during this intermediate iterations. Okay, so that seems like a deceptively simple change, but let's contrast this to SQP. So remember the problem with inequality constraints that we saw with the KKT conditions. What was the big problem we had? So with equality constraints, it turned out not to be too bad. The KKT conditions were just a set of nonlinear equations. We could iterate and solve them. But with inequality constraints, we had these complementary slackness condition. And really, all it told us was that the constraint was active or inactive, right? It said the slack is 0 or the constraint is 0. One of them is 0, but we don't know which one. That doesn't really give us any information. So we have, in some sense, now fewer equations and unknowns. We can't solve it directly. And so there are two kind of main approaches here. Of course, many variants between them. One is what SQP does, which says, okay, look, there's all these constraints. Some are active, some are inactive. I don't know which ones are. So I'm going to try to estimate. I'm going to try to use this idea of an active set. I'm going to try and figure out which ones are active. If I know which ones are active, then I can ignore all the others. And all those active ones I treat as equality constraints. And now I have an equality constraint problem. I just use everything that I'm used to. All right, and then in the next iteration, I'm going to update my estimate of the active set. So that's one idea of the SQP, is that let's try to figure out which ones are active. Let's distinguish between active and inactive. Interior point is different. It's saying, you'll notice here, I have no inequality constraints. I just forced everything to be an equality constraint because I have this slack variable now. And this slack variable is dealt with this barrier. So there is sort of this inequality that exists now, but I've forced that to just kind of happen naturally. I didn't actually have an inequality in this problem. The log is just going to force that. I've just created this barrier that nothing can cross. So it acts like this inequality constraint, but it's kind of by design in the formulation of the problem. So now all I have is equality constraints, and that I know how to solve, right, without having to do any combinatorial problem. The downside of that, though, is that I have to consider every constraint, right? I've put every constraint here, whereas with the active set method, I could have tons of constraints, but if many of them are inactive, I ignore those ones, right? So there's kind of a trade-off. There's maybe more work trying to figure out which one is active or inactive, but as I establish that, I work with a smaller problem. Here, I don't have to deal with that bouncing around about trying to figure out which is active and inactive. I treat every constraint the same way, but I have to treat all of them. So what we would do, of course, is what we did before, right? We create a Lagrangian, have a Lagrangian, and that's going to be f of x, right? My objective, and then I add my well, okay, let's try this way. We'll add all the Lagrange multipliers times my equality constraints. I guess I should do j since that's what I did above. And then I'm going to do the same for these. Oh, sorry, I didn't write the full f. I better write all of it. F minus mu natural log of s. That whole thing is my objective, right? That's the objective. And then I add a sum of the equality constraints. And then these ones are actually now also equality constraints. We'll just use the same symbol we've been using for inequality, which is a sigma for that Lagrange multiplier. And then I have g of k plus sk. Okay, so I've now created, because they're all equality constraints, I can just form this directly. I have, let's see, I've got x, I've got s, I've got lambda, and I've got sigma. But I can take all those partial derivatives, set them equals 0, just like we did before. And I can apply Newton's method to those nonlinear equations and solve those KKT conditions directly. So in other words, it's a lot like what we did with the equality constrained SQP approach. So that's the idea. For implementation, there are, of course, other various details that are important. For example, we mentioned that we need to update mu, right? Mu needs to, this isn't really exact until mu goes towards 0. So we're still have to solve a sequence of problems, or we're solving a sequence of problems anyway. So we're going to do that by taking mu smaller and smaller. We are going to still need, an estimate of the Hessian of Lagrangian, really. And just like we did with unconstrained optimization, there's quasi-Newton methods to do that. Same thing that happens with SQP. But this is the basic idea, right? It's kind of these two approaches, which is to deal with this problem where inequality constraints are hard. Either we try to guess and figure out which ones are active and inactive, and just ignore the inactive, make all the active ones equality constraints, because that's effectively what they will be at the solution. The other is we just make everything equality constraints, and we do this by this nice trick of having this slack variable that allows this to be satisfied with this implicit inequality that's dealt with by this barrier function. It's going to force us to stay on this interior region where we're always feasible, at least feasible relative to these slacks. One last thing I want to mention, this occurs for both SQP and interior point. And I should say these two methods, these are the most common ones you'll find. So often in many solvers, you'll have options between them. And it's good to have these options because it's not clear beforehand what's going to be the best algorithm. I mean, there's some general rules of thumb. SQP tends to be more effective if you can provide a better starting point. Interior point is maybe better if you don't know anything. It's a little more, it may be more effective in that approach. Well, yeah, anyway, there are various rules of thumb, but I would say it's really kind of problem dependent. Some people say the interior point's better for large scale, or that's better if you can provide second derivatives. But again, it usually comes down to some testing, what's right for your problem. Here's the last thing I just kind of want to touch on. Just want to mention this idea. Won't get into too much detail here, but I want to mention another place that penalty functions occur. And this is in what's called a merit function. So here's the idea. When we solve this this problem really, when we take those derivatives 7 equals 0, we get a set of the KKT conditions. And we solve that iteratively. And at each iteration that we solve it, we're going to get a step. Same thing in SQP, right? We get a step to move, just like we did in unconstrained optimization. But also, just like we did in unconstrained optimization, we don't just accept that step. Generally, we're going to do a line search. So we will look at that step, and if it satisfies our criteria, we will accept it. But if not, we're going to backtrack because we know, of course, that our estimate for the gradient, Hessian, and all that are really only good locally. As we go too far away, we know it's a bad approximation. So if the point that this iteration tells us to go to is not good, then we know eventually if we back up, we should get a good point. And as we saw, also sometimes there's reasons to go forward. But anyway, here's the idea though. For unconstrained optimization, we could just look at the objective because we knew if the objective was decreasing every time, right? We're always guaranteeing that no matter what, we're always only going to accept something that's decreasing the objective. We had some sufficient decrease criteria. Eventually, we'll get to the minimum. For constrained problems, that's a little bit harder because we actually now kind of have two things we're balancing. We can't just decrease our objective. What if the objective decreases at this new point? It's a great decrease in the objective, but our constraints become more violated. Or what if this new step really satisfies our constraints much better? There's less violation, but our objective increases. And often these two things do compete. And so we need some way to combine them, right? And of course, the Lagrangian is kind of that idea, but especially early on in the optimizer, the Lagrange multipliers, like we have no idea what they are, right? They're just a guess and they improve as we get towards the optimum, but that's not a very robust thing. So often what's used is either like an augmented Lagrangian where we take the Lagrangian and we add a penalty term to it, or just a penalty function. So for example, here's some merit functions. You'll recognize these because they look exactly like the things that we've done. F of x plus mu times, I'll just do the inequality constraint, although you can also do the equality constraints, right? And it could be squared, it might not be squared. It's less important for the line search because we're not like, doing derivatives along the line search per se. We're just taking these sort of discrete jump steps. So it could be something like that, right? This could be a merit function that's used, or we could do this augmented Lagrangian, which takes what we currently estimate as the Lagrangian. So actually, I'm just not going to put the inequality. I just want to keep this simpler here. Let's just do the equality. Let's just say h squared. Okay, and in this case, we could do the Lagrangian. So often that's usually not enough though, right? Because our Lagrange multipliers aren't very accurate. So this is what the augmented Lagrangian looks like. We could do something just like kind of like above. We would add them both. So anyway, there are various options here, and these don't have to be squared. Like I said, it doesn't really need to be smooth. Sometimes you'll just see an absolute value. Could be squared. There are a lot of variations here. But the idea is this, that we can no longer, in the line search, just look at the objective, because that alone won't tell us if the point is better. We need to combine them some way. So this is another motivation for where the penalty occurs. We don't use the penalty directly in our optimization, but we just use it as kind of this criteria during the line search to say, is this point good enough to move on? We don't really need tight tolerances here, because this is not where the real optimization is occurring. This is just to say, is this good enough? Let's, go to the next iteration. Okay, so that's really it for constraint optimization. There are a little bit more algorithmic details in the book on both SQP and interior point, and of course in the literature, if you're really interested in diving into the details of these, there are a lot of various considerations that are needed to make these robust. And this is why there are these commercial tools, because they're actually fairly complex if you want to develop a really robust solver for these general constraint problems. All right, so next time we're going to jump into the gradient free world, so that'll be interesting. We'll see you then.